This conference will now be recorded.
Okay. So good evening and welcome back to fresh new session of market risk modeling with Mini. So one of the important, so we'll just pick it up from the point where we had left it off in the last class. So in the last class we had been discussing about the augmented decoupleur test and the decoupleur test, and we talked about the structural break. And in short, so what we started looking into was how is it that the stationarity can be tested in the presence of a structural break. What are the steps that we can take in order to solve those problems? And then what we also looked into was that assuming that I identify that a system is non-stationary, then how is it I can help convert it into a stationary system, right? And in that respect, we looked into two things, one of them being the trend stationary process and the other being the difference stationarization. So one being the trend stationarization and the other being the difference stationarization. So one thing that we could see from there is that yes, we could actually work with them in this particular manner. So we could actually work with those in this way. Right, so we could help solve the problem of of non-stationarity by either trend stationarizing the process or by different stationarizing the process. So that is something that we had kind of looked into the last day, and with that, the more or less the key aspects of stationarity as a concept have been covered. So before we move on to the next part, the question that we would like to talk about over here is that how is it that a stationarity is identified? Or first of all, what exactly stationarity? Why is it important? How is it identified? What are the different ways of identifying stationarity? And once we identify, so how do you identify stationarity in the presence of a structural break? And then the next thing is that in case we identify a stationarity, how do we solve the problem associated with stationarity issues? Right. So that is something that we had looked into in the last class. Now, once the time series has been stationarized, right, we need to estimate the time series. So we need to identify what type of a time series is it. So is it an autoregressive process with a moving average process, or is it a combination of both? Right. So now from here, the questions of estimating the time series model comes in. So first, we identify that whether the system is stationary or not. Next, what we do is we try to identify on the stationarity series, we try to identify that how is it that the model's prediction is working. So how is it that we can predict from the time series model? So that is the next thing that we would generally talk about, right? And in order to talk about that, two very important concepts need to be introduced, or two important concepts will come into play. And these two are the two components of a time series model. And what are those components? Those components are the Ar process, that is the autoregressive process, and the moving average process. So that is the Ar and the Ma processes. So these are the two processes that we need to talk about. We need to understand the key characteristics of these approaches. We need to understand the key estimate. What are the ways in which the regression coefficients for an Ar model will be estimated? What are the methods using which uh, the regression coefficients of the MA process will be done, and what are the key characteristics? So what are the criteria for an Ar process to be stationary? What is the criteria for a MA process to be stationary? So if both these two criteria is there in the system, then we know that the final model that we have developed is a stationary model. Right. So these are some of the questions that we need to address or need to address in this section. Right. So we need to understand that, okay, if there is an autoregressive process, how to define that process, how to generate the data, how to create the data generating process of the TGP for an autoregressive process, what are the key characteristics or what are the key moments of a autoregressive process. Similarly, what are the processes of a moving average process, and also these are some of the questions that we would look into, right? And if an autoregressive process is stationary, how should the what should be the patterns of the ACFs and the PACFs? So the autocorrelation function, the partial autocorrelation function, right? How is it that we represent time series model with, so if it's an AR2 process, how is it that the ACF and the autocorrelation function and the PACF should be calculated, right? How should they be interpreted? What are the conditions that must be there? So these are some of the questions that we would need to understand when we are trying to develop the or the ARIMA process. So when we are trying to develop an autoregressive integrated moving average model. So, but before integrating a moving average and autocorrelation together into one, so let's start by talking about the autoregressive portions, right? So we need to understand the autocorrelation function of an AR process. We need to understand the partial autocorrelation function. What exactly, how is it that an AR model is estimated, right? How is it estimated? Why is it estimated like this, right? So these are some of the questions, or how is it that an MA model is estimated, right? So these are some of the questions that we need to talk about, right? Then obviously from there we'll see how that once that estimation is done, how is it that the forecasting is done. So there are different steps of developing the model. So we have till now covered the first step where we have seen how the identification is done. Now we are moving to the estimation step and we are exploring the two most important components of a time series model, which is the AR and the MA model, right? So that is what we want to develop. Okay. So let us start off with by talking about this autoregressive process. What is this autoregressive process? How does it look like, or how is it represented, and so on. Okay, fine. So we'll start off with the autoregressive processes. The autoregressive process. Okay. Now over here, one of the most important things that we have is, so let us first represent, or let us first look into the mathematical formulation of the autoregressive model. So the over here, the in an autoregressive model, the yt is explained by the historical values of yt. rho k yt minus k. So what are the things that I have over here? I have rho 1 yt minus 1 plus rho 2 yt minus 2. Like this, I have rho k yt minus k. So over here, what we are seeing is that for an autoregressive model, the yt, right, or the dependent variable, is being explained by the historical lags of the dependent variable. So plus the random error term ut. Now the ut is a white noise. So ut follows normal distribution, mean 0 and sigma square u. The ut follows normal distribution with mean 0 and sigma square u. Right. So this is what the yt is. Now the objective over here is, now this is the level form, right? Now there is also a way to describe these autoregressive model as a deviation form, right? So if you have a long run mean, you can express the autoregressive processes as a deviation from the long run mean, right? So this is what we call the level form of specifying an autoregressive process. So in this part, what am I doing? I'm saying that okay, yt is y1 is this, yt is this, yt minus 1 is this, yt minus 2 is this, and you have a level form, right? So there is, so this is in the level form. Now, apart from the level form, there is a second form which we call the deviation form. So over here, what we have is the following: yt minus delta. So let's say there is a long run average value, long run average mean, from which I am looking into the deviations. So what I'm now in this second form that I'm specifying over here, I'm not trying to model the values per se, but I'm trying to model the deviation from the values. So what I'm trying to do is I'm trying to predict that okay, there is this series yt from delta 0, right? So delta 0 is the long run mean. What I'm trying to do is I'm trying to find out this deviation. I'm trying to estimate this deviation from the long run mean yt. Right. So this is your rho 1. It is yt minus 1 minus delta 0. Right. So like this, I have rho k yt minus k. Delta 0. This is plus ut, where ut is a white noise star. So ut follows normal distribution with a mean 0 and sigma square u. Now this is the part which is the level form, right? Now from the in the level form, the next thing that comes with this is your deviation form. This is your deviation. So these are the two types of autoregressive, so the two alternate ways of working with an autoregressive process, right? Now, once I have looked into this process and once I have gone through this, the next thing that comes out to me is the following. That I have talked about an autoregressive process, I have defined the process. But the question that comes out over here is, or like any other, so the biggest challenge in the process is to estimate these row hats or the hat of these rows. The question is that how easy that I can estimate this row hat. How easy that I will estimate the row hat, right? How do I estimate this? Now the question that comes out over here is that so what is the estimation process? The estimation process that we will use over here is the one that we have already discussed, and that is the OLS, or the ordinary least square estimate. So this is the OLS estimation, right? So this is the OLS estimation. So over here, when I talk about this estimation process or something like that, or something like that sort, so the OLS estimation that I am talking about over here. So that is the one that we had discussed while we were talking about the linear regression models. But even before we talk about estimating the row hats, a very important question which comes out is that we want, or what we want to investigate over here is the data generating process, or the DGP of the time series, or of an AR process. So for an AR1 process, what should be the data generation process, or the DGP of the AR1 model? So like when we had worked with the random walk model, right, we had seen that yes, the data that the the data points which are being generated, the data in the data generation process, the data points which are being generated are the ones which is, so the data generation process is the one which is like the data generation process is the one which is which through which you can successively you can generate the data point. So this data generation process is so as we saw it in the random variable, or the random walk process exercise, can be obtained as an iterative output, can be obtained as an iterative output. Iterative output. So through an iteration process, we can actually obtain the data generation process. So the data generation process of an of an autoregressive time series model. Now, for performing of a calculating the data generation process, what we are going to do is the Ar1 model. So we'll start off with the Ar1 processes. The Ar1 process. So let us first explore the data generation process or the data generation model for a Ar1 process. Okay, so let us start off with that part first. So the first is that we need to specify a Ar1 process. Now, when I say that I need to specify an Ar1 process, by that what I mean is that I need to find out a way to define the Ar1 process first. So I need to mathematically specify this Ar1 process. So how does this Ar1 process look like? The Ar1 process looks like the following. That is Yt is equal to rho 0 plus rho 1 y minus plus follows normal distribution in sigma square. Right. So Yt is equal to rho 0 plus rho 1 Yt minus 1 plus Ut, where Ut follows a normal distribution with mean 0 and a variance sigma square U. Okay. So yt equal to rho 0 plus rho 1 yt minus 1 plus rho 2. Right. So okay. So now the question is that how do I assess or how do I obtain the data generation process? Now, the data generation process will be derived in a very similar manner like that had been done previously. So we'll start off with at t equals to 1. Y0 plus U0. Now, if you have a look, U0, Y0, Y0 plus U1. Right. So now the next question that comes out over here is that yt is equal to, so over here I have yt equals to rho 0 plus rho 1 y0 plus u1. So I am evaluating this at the time t equals to 1. Now similarly, I will, if I resolve this equation or if I try to solve this equation at t equals to 2, right? So y2 over here is rho 0 plus rho 1 y1 plus u2. Now you will observe that y1 has been solved over here above, right? So this y1 can be used to, you can put this y1 over here and iterate, or you can substitute y1 with this value and you can iterate that. Y1 is equal to rho 0 plus rho 1 y0 plus u1. So if I solve this, you will see that it becomes rho 0 plus rho 1 into rho 0 plus rho 1 square y0 plus rho 1 u plus u. Right. So one of the most important characteristics that we can see over here is the following: that at every iteration, so when you put it in 3, put it in 4, and put 3 in 4, then put that 2 in 3, and it keeps on going on like this, right? So there is a very iterative process which will help us generate this thing. Now, if I put this expression at t equals to 2 into 3 and solve it, so I'll get another form in terms of p0, p rho 0, rho 1, and so on. Right. So there is a iterative form. So therefore, there is an iterative form to this particular problem. So the question that comes out over here is that what then is the general functional form that this autoregressive process would have? Right. So what would be the most general functional form that it would have? The most general functional form, or the basic data generating process for YT is rho 0 is summation I equal to 0 to t minus 1. Rho 1 t y0 plus rho 1 to the power of I into ETR. Now let us interpret this mathematical form that I have written over here, right? Now what is it saying, or what exactly is then the interpretation of this time series? So it says that the prediction that we are making for the period YT, right, for the TH period, is determined by three major components. Number one is the rho, that is the correlation that's the autocorrelation coefficient between, or that element of responsiveness or causality between YT and YT minus 1, between two lags, between a lag and YT. So it is determined by the rho i's, so by the respective rows, right? The second thing which impacts this is the y0, the initial condition, and obviously there is an impact of the error terms, right? So these are the three broad components in the data generation process. Now when we talk about the data generation process over here, one of the important things which becomes very important, so one of the important things is that the rho i's that I have, it is the additional impact of the rho i's. So if, let's say, this lag YT minus 1 has an impact of 0.02 with YT minus 2 has 0.01.15 with YT, 0.013 is with Y2, YT minus 2 with YT. Then it is the sum of all these impacts, right? Which is, I mean, to the power of that lag. So basically, as the lag increases, the impact keeps on reducing, right? So it is that impact which is the cumulative impact, cumulative historical impact which is impacting YT, right? And the second thing is that the row one, that is with the row one is the autocorrelation of the slag YT minus one with YT, right? And the third thing is that third is with the error terms. So the error terms are also kind of uh, impacting the measure of YT because higher the error component. So in the past, right? So that will take a longer time to weigh now. So, but when I'm talking to the error terms, right, the historical error, so that is also that comes in or that comes in as a product with the row one ice, right? So that is where this so that is where over a long run period the impact of the error is gone. Why? Because if I look into the expectation of YT, if I look into the mean that YT would have, right, that expectation of the error will become zero. So the third component, the cross product or the cross impact of row one and the error term will not be having any average impact. So all the average impacts will get cancelled out. So what would impact is the true associate, the true extent of causality between two lags and their sum product, their total sum, the cumulative impact, as well as their initial conditions, the point from where is that this thing is starting, right? So what is the initial value from where it is starting? So the initial value has an important role to play when you are trying to develop an ARIMA class of a, or you are trying to develop an AR class of a model. So that part remains very useful over there. So now there are two things. Now I need to understand that when is it or how is it that this time series or under what conditions will this particular AR time series that I have written over here, this will become stationary. So under what situation will this become stationary? Under what circumstances will this become stationary? So this is something that we need to understand. Now, if it is to become stationary, first of all, what we must do is, or what we must keep in mind is that the mean has to be constant. So the conditions for stationarity will involve those conditions where the mean becomes constant or the mean, yeah, so where the mean becomes kind of constant. So that is something that we need to understand. So when I talk about the stationarity, so first of all, what we do is we calculate the expectation of YT. So what exactly is the expected value of YT? Now, when I take expectation over this error term or the stochastic component, ET minus I goes for a toss. So that part becomes zero. So the only thing which remains over here with me is the following. That is row 0 plus, Hello. Yeah, am I audible now? Can you hear me? Okay, perfect. Okay, so as I was saying now, right? So this is what which becomes after the expected value of the series is taken. So now, if I think about this this equation that we have written over here, if I think about this expected value of yt series. So now, if I break this series, what will it be? If I break or if I expand this series, it comes to the following. So you have row 0 outside this. This is 1 plus row 1 plus this is row 1 square. So these are all the cumulative impacts, right? Like this, if you go ahead with it, it becomes rho 1 to the power of k. Okay, so one thing that you can see is that this series or this series of row is in a geometric progression, right? So therefore, what we have over here is something like this. Have row 0 into 1 minus row 1 to the power of t divided by 1 minus rho, right? Plus rho 1 to the power of t y0. Now there are two things that we need to keep in mind. Number one is that if this mean has to be a constant mean, then first of all this second part must tend to 0, and this row, the absolute value of the, I mean, this must become a constant. Only then will you see that the mean becomes constant. So now the question is that under what situation will that happen? So what I want to do over here is the following, that as t tends to infinity, right? So as t tends to infinity, it is the tendency, it should be the tendency of this time series to converge, or this mean to converge to a constant. So as t tends to infinity, one of the thing that must happen is rho 1 to the power of t y0 must tend to 0, right? And also what must happen is that this rho 1 to the power of t must tend to 0, right? So this, and the expected value of yt must tend to a constant. must tend to a constant. Now the question is that under what circumstances will this be possible? Under what circumstances will this be possible? So this will be possible only when mod rho 1 is less than equal to 1. The mod rho 1 is less than equal to 1. Right? So if each of the row i's are less than 1, if the mod row i's are less than 1, then we'll say that. So if all these, because it's an AR1 process, right? So therefore it is row 1 only. So if the row 1 is less than equal to 1, then the mean converges to a constant value, and hence it is seen to be a stationary time series under this assumption. So the condition for stationarity of an AR process is that the row 1 or of an AR1 process is that the more that row 1 must be less than equal to 1. Okay, so mod row 1 is less than equal to 1. So if the rows are unity, right, or less than equal to 1, then the expected values of yt, then the expected value is, or then the mean converges to 1. Okay. So this is more or less the so this is basically the condition for stationarity. The condition for stationarity of an AR1 process. So condition for stationarity of an AR1 model. Of the AR1 model. Now this model states that, so therefore the first condition for stationarity of this AR1 model is that mod of rho 1 must be less than equal to 1. So there, sorry, must be less than 1, not less than equal, less than. It is less than 1. Right. So therefore, generally, it's so because we know that if it becomes equal to 1, we end up with a unique loop process. And if it exceeds 1 the time, it becomes mildly explosive. So therefore, it is very important to have this kind of a this kind of a setup. So this is so therefore, how does the mean now look like? So after so if the row ones are less than 0, then this converges to row 0 by 1 minus row 1. Right. So this is right. So any questions up to this point, Badmi? Perfect. Now the next question that comes out over here is that, so this is the mean, right? Now the question is that what is then the variance of this process of the AR1 process? Now, so if the time series has to be stationary, so then we must have both the mean and the variance as stationary. So this is where we need to look into this. So the variance of the time series is nothing but, so how do we calculate this? So we calculate is we look into the sum square of the deviation from the mean. So this is the expected value of yp minus mu whole square. Right. So over here yp minus mu. So basically, if you think about it, if I look into this equation, right? So the variance yt minus mu is nothing but, so this part becomes rho 0 minus this, right? So and this is the one which is your variance. So this is the part which remains as the variance. So basically, if you look into this equation, so expectation of yt minus mu. So yt is nothing but minus rho 1 plus the summation of rho 1 I e to the power of t minus I whole square. So if I'm trying to do this, so the next thing that comes out over here is that rho. So therefore, yeah. So rho minus I minus rho by 1 minus. So this is the mean, right? So both these two part would cancel out, and we would be left with this one. This is summation rho 1 I e t minus I the whole square. Okay. So over here, so if I solve this, right, so if this is solved, then what you get is something like this. You get sigma square. Now sigma square is a constant mean by 1 divided by 1 minus rho 1 square. So over here now rho 1 is something we know that if the time series the mean has been stationary, right? So then rho 1 is a fraction, right? So it's constant. So sigma square into 1 by 1 minus rho square is also a constant, and hence what you would see over here is that the times here, so the variance is also constant. So basically the mean and the variance becomes constant if the rho 1, the mod value of the rho 1 is less than 1. Right. So this is the condition or the criteria for an AR1 process to be stationary. And these two are the respective moments of the stationary time series. So if you remember when we saw the when we saw the random walk process, we saw that it was y0 or the so it was y0 or the initial condition, because the mean which was constant, and then there was a trend in the variance. But over here you see that that particular trend is not there for a univariate series, and the mean is actually constant, right? So so this is how we reach to the conditions for stationarity of an AR1 process, right? So is it clear up to this point? Okay, perfect, perfect. So let's take a pause here for the day. So basically, we have covered the AR1 process, the auto-regressive process today, the conditions for stationarity, how the model is being framed. So just go through this discussion session today, right? And we'll have a session on Friday. Friday is 2nd October, right? That's a holiday. So even I think it's a holiday at your end as well. So the session that we missed out yesterday, we will do it on Friday, and we'll have it on Saturday and Sunday as usual. So we'll be able to cover up this ARIMA model by next Sunday, because Friday I'll do the MA process, and then we'll see on Saturday and Sunday in SAS that how is it replicated and how is it developed in SAS. So that will cover the first bit of time series for us. Thank you.